Okay, just going over some basics that will help a little bit later on. Now that we're in senior chemistry, this is probably more junior science. Fixed shape and volume, fixed volume, no fixed shape, no fixed shape, no fixed volume with classical definitions. There's a little bit more about being compressed or can't be compressed. That's the real difference between gases and solids and liquids. Gases cannot be compressed, can be compressed and expanded very easily because they don't have much attraction between the particles, whereas liquids and solids, they are quite close to each other. So these ones just vibrate and these ones just roll over each other. So what we're really going to look at now, so that's really getting to more advanced, so talking about how the particles vibrate and rotate, and this one, vibrate and rotation's not really the thing. They're really zipping around in empty space in an ideal gas with no attractive forces between them. So what you really need to do with senior chemistry is you need to get specific and you need to talk about what sort of bonding there is, if I can find my pen. And so even this one here we could expand on. And so the reason why they have different melting points, boiling points, is because of the types of bonding. So if you need to look at the different types of, you might not be up to this yet, but when you get up to the different types of intermolecular forces or the different types of bonding which are stronger than these, such as ionic, metallic or covalent, you'll talk about what sort of bonding is between the particles to determine whether their liquid melting and boiling points are very strong or what state they're in. Okay, so number one, always talk about particles. I'll write that up here. Number one, always talk about particles and then talk about the types of bonding between those particles. So just a revision on the basic terms. So sometimes you'll see solidification here and liquefaction, but the proper terms are melting and freezing. Deposition is just jumping states, going straight from a gas to a solid or a solid to a gas. And a little bit more tricky is the vaporization, so going from a liquid to a gas. So boiling is when the vapor pressure outside the liquid is the same as inside the liquid, and so you can get liquid turning to gas throughout the whole liquid. You can do that by heating the temperature up of the entire substance so that the vapor pressure can form within the liquid, or you can put it in a vacuum and decrease the outside pressure, and so you can get water to boil at very low temperatures, even 0 degrees. So the difference with evaporation is no external heat's been added to it, and it's just liquid escaping from the surface, not throughout the entire liquid. So boiling and evaporation are different to each other. Vaporization covers both terms. I probably should also note that evaporation can occur at any temperature. Boiling occurs at a particular temperature. And as we're going into pure substances and mixtures, it's important to note when it's a pure substance, it'll have a very specific melting point and boiling point, which are here on these straight lines. And I'll explain this diagram a little bit better in the next slide. Just touching on this one now. So we use Kelvin in chemistry, which is the same as Celsius, but adding 273 to it. So 0 degrees Celsius is 273 Kelvin. Water boils at 100 normally, so water boils at 373 Kelvin under the right conditions. So what you'll find here is, I can't draw on this unfortunately, so you just have to look at my arrow, that the energy that goes into the system at these points, it's always a solid, so you just should see an increase in vibrations of the particles. Here you should just see an increase in the particles rotating over each other, and here you shouldn't see an increase in the particles zipping faster. So an increase in temperature is an increase in average kinetic energy, so that you should see the particles move faster. In these stages here, you shouldn't see any change in the movement of the particles, vibrating or rolling over each other, or rolling over each other and the ones that have escaped. But technically none should be escaping here, and none should be escaping here just a slight evaporation that's normal, maybe a slight increase in evaporation because the temperature is increasing. But here all the energy is going into breaking the intermolecular forces usually. There could be other forces, breaking the stickiness, the bonds between the particles to change the state. So if I move this along, you'll see down the bottom here that this is ice, and you'll see that it should always remain ice. And as you see this little red thing go up here, so you look in here, you can see the temperature increasing, you can see the rate of vibrations increasing, and you can see it remains as solid. So this is what's going on according to the particle theory. And then once we get to this stage here, you shouldn't see any increase in the rate of movement, average rate of movement of the particles, but instead all the particles have gone from just in fixed places vibrating to being able to roll over each other. Okay, so you can see down in this cup here, it's going from a solid to a liquid. So you're looking at three things here as we're going back and forth. Now, as we go here, I don't really like it that this simulation actually has liquid converting to gas. Fair enough, it would be a touch of evaporation, but that's just way too much comparatively speaking. So I'd like none of those particles to come off, and all you're getting is an increase in increase. So it's still liquid down here in the beaker here, and all you're getting is an increase in rollover. Now, when you get down to these last four particles here, you can see that the liquid is completely turning to gas as we go back and forth. And so the temperature is staying the same, so they should be moving about the same space, and now everything has gone to gas. The temperature can now increase, and as I go up, the rate of movement of the particles should increase. Okay, so you just need to know that as energy goes across, when it's in one of the states, the energy that goes into the system goes to increasing the temperature. But as soon as it hits the melting point or boiling point, the temperature stays the same because the energy is going into breaking the intermolecular forces usually, or the forces between that's holding those particles together.